And we have a really exciting lineup of speakers this semester, so I hope you'll all coming back. Today, I'm very thrilled that we have Scott Lindeman from the School of Engineering and Applied Sciences. And Scott is a PhD candidate, and he works with Ryan Adams and Leslie Valiant. And he's a member of the Harvard Intelligent Probabilistic Systems Group, also known as IQSS. They have a very cool blog. You should check it out. Scott's work on network topology was presented earlier this year at the Computational and Systems Neuroscience Conference, and I hear it was quite well received. And today, Scott will be talking about an extension of some of that work, specifically looking at how Hawk's processes can be used to model spiking data. So it sounds really cool. I got a little preview of some of the pictures of the slides, and I'm really excited. I think you will all really enjoy this talk. So, one quick note before we turn it over to Scott. Since it's the first meeting, I like to just throw out the rules of the game. We like to be a fairly lively crowd here, and Scott has said he is welcome to have anyone jump in at any time. So if you like to jump in and ask questions, feel free. If you're like the political scientists who like to politely wait and then applaud and then go for the jugular afterwards, that's also an option. We'll have a Q&A afterwards, so you can save your burning questions for that. In any case, we look forward to having a discussion and lots of involvement. So, see that. And then, without further ado, I will turn it over to Scott.
Thank you, Tess. And thank you all for coming. It's really a pleasure to be here. It's nice to get out of Maxwell Dworkin and to interact with the broader community. And I hear that it's the first talk of the semester, so I'll try to get my starting line. Today I'm going to be talking about discovering latent network structure and spiking data. And in particular, looking at data sets like this, upticks and downticks on the Standard & Poor's 100, and asking, do stock prices move independently from one another, or do they move as a sector? Or questions like, does activity on one stock predict subsequent activity on other stocks? To look at another domain, thinking about gang violence in the city of Chicago, and asking, do homicides in one gang region incite retaliation in rival territories? Is this something that we can model with statistical models? In order to do so, we will leverage tools from computational neuroscience, which is my area of expertise. And we'll be looking at specifically point processes for modeling, in this case, in the computational neuroscience case, for modeling action potentials, and thinking about how action potentials excite others, according to these intricate neural networks. We'll also leverage tools from social network analysis in cases where we observe some patterns of interaction and maybe some properties of the different nodes in this network, and ask about the generative processes or the rules by which this network came into being, or to reason about, for example, latent properties. So in social network analysis, if we have a good model of how networks come to be, then we can ask questions like, if we observe interactions, what might the latent properties of these nodes be? In the previous example, things like, were these nodes male or female, or did they belong to one group or another? But in the neural case, and in some of the other cases I'll be talking about today, we actually don't have direct ability to observe these interactions. Instead, we perhaps see events that occur on these nodes, noisy emissions from each node, and we think that there might be some interaction between these events which would allow us to infer the presence of these latent interactions. So, with that introduction, the order of operations for today, we'll start out by talking about random network models, statistical models that we can use to reason about the different distributions over random networks. To model the point process aspect of this noisy emissions, we'll use something called Hawk's processes, which are a class of mutually excitatory point processes. And then I'll talk about how, given this joint model that includes both network structure and Hawk's process dynamics, how can we do inference in this large and complex setup? And we'll be using Markov chain Monte Carlo for that. And then finally, I'll conclude with some example applications. So to begin, perhaps the simplest random network model is something called the Erdős-Rényi model, developed back in the 1950s. And in this model, basically every interaction here, which is going to be an entry entry in this matrix. An interaction will be directed. It will go from some outgoing node to some incoming node. And we'll say that an interaction is present with probability p, independently of all other interactions. On top of that, later we'll add in some strength of interactions, which would correspond to the scale bar on the right here. We can introduce more sophisticated types of interactions or types of networks by thinking about things like stochastic block models, which say that the probability that there exists an interaction between two nodes is a function of the class assignment of those two nodes. And in some cases, we may actually have observations of what these classes are. Perhaps it's a tribe in the social network case. In other cases, that might be something that we wish to infer by looking at consistent patterns of where interactions exist. Another class of random network model that we might wish to leverage, and that might be, for example, useful in the Chicago example, is to think about latent distance models. So the probability that an interaction exists between two nodes is a function of how far apart they are, either in some real space, maybe it's geographical space, or maybe it's in some latent future space. Again, these are things that we may have access to or that we may wish to infer. So in this example, the outgoing nodes and incoming nodes are ordered according to their location along some one-dimensional space and distance. Or you can see that connections are mostly clustered around shorter distance nodes. So these random network models can all be unified under one very nice and coherent framework, thinking about exchangeable random graphs. And there's recently been a rich set of literature on this space that's made its way into the machine learning field. And there's something called the Aldous-Hoover representation, which allows us to unify all random graphs which have this exchangeability property, namely that if you relabel the nodes in this network, that the distribution over the interactions that you were able to change. So in this case, the random network models are going to express our hypotheses about what patterns of interaction may exist in real-world networks. The Hawkes process will be the point process model that allows us to link those hypotheses with the observable data that we collect. So are there any questions so far on the random graphs or anything like this?
Can you elaborate a little bit more on exchangeability?
Yes. So the Aldous-Hoover representation is somewhat analogous to the DiFinetti representation, if you're familiar with that. And the idea is that if I take some social network, for example, and I label all of the nodes 1 through n, and then look at the distribution over the edges between those nodes, that probability of that set of edges would not change if I were to permute the node labels. You could say, instead of calling me 1 and somebody else 2, call me 2 and somebody else 1. So that's the simple intuition behind the exchangeable random graphs. And there's a much, or between Aldous-Hoover representation, I should say. And there's much deeper literature on this that we could go into perhaps.
But if we had like covariates about particular nodes, someone's a male, someone's a female, someone lives in this neighborhood, up to like what the information about those covariates, then they're exchanged.
Yes, and so if you permuted them and kept all the covariates. Okay, so that's the random network side of the story here. The Hawkes process side of the story. In order to get to that, we'll have to start with very basic high-level point processes. So point processes are a really foundational statistical object. They give us random subsets of a larger space. So for example, random subsets of time, spikes in time, or events in time, or random subsets of space. These things have been used to model earthquakes, for example, disease outbreak in epidemiology. In computer science, we like to use point processes to model the arrival of customers in a queue or the requests for access to some web page on a web server. The point process that you're most likely to have encountered is the Poisson process. This is the simplest of point processes, and it's characterized by a rate function lambda of t, and the fact that disjoint regions of space or time in this example are independent. So the number of events that I receive in one region of time is independent from the number of events that occur in some disjoint region of time. And moreover, the number of events that we region of time is the integral of the rate function over that time. So that would correspond to this area, this shaded curve here. And there's one important fact that we'll leverage later on, the Poisson superposition principle, which says that the sum of independent Poisson processes with rates lambda 1 and lambda 2 is itself a Poisson process with rate equals the sum of those two rates. But one of the shortcomings of the Poisson process for modeling real-world examples is exactly that it does not have dependence between these disjoint regions. So if we are trying to model something like relationships between homicides in Chicago or upticks and downticks in the stock market, then we would like to capture the effects that one event has on the firing rate subsequently. And Hawk processes give us a way of doing so. They're multivariate point processes in that they describe events that occur on more than one node or more than one process simultaneously, and they allow us to have exactly this event-driven dynamic. Perhaps the easiest way to see this is with a visual example. So in this example here, there are 4 processes, and there's a chain, and the network is shown on the left side here, so this is chain. The first process is going to connect to the second process, or node, I should say, the second to the third, and the third to the fourth. So we'll assume that there is some background rate of events that occurs on the first process. And maybe from this background rate, we get one spike first. This spike will induce a kernel, a temporal kernel onto the second process. And then from this kernel, we'll draw spikes according to, in this case, an inhomogeneous Poisson process. So this kernel will perhaps excite the second node. There'll be one spike from that. The second node will induce the kernel onto the third. And in this case, perhaps there's 2 spikes that are drawn from it. The number of spikes that's induced is, again, going to be an expectation of the area under that kernel. So there's 2 spikes here, events that each induce kernels onto the fourth process. And then, since there is no connection going from the fourth process to any of the other nodes, these 2 spikes don't affect anything else. And then perhaps other events occurred on the first process, which again caused some similar chain of events. Now, in this case, the network was quite simple. There's just a chain, and all of the interactions have the same strength. The kernels all have the same area under the curve. It could be more complicated. For example, what if we have different interaction strengths between these nodes? So the first to the second interaction is considerably stronger than the second to the third. In our picture, that would correspond to kernels which are simply shifted or scaled up or down in this case. So the temporal response profile is going to be the same, where it's going to scale the area under this curve according to the strength of interaction. 3 spikes are generated, each of which induces a smaller temporal kernel onto the second, or onto the third process. Perhaps only one is generated as a result. And again, we can continue this process. So the Hawk's process is a way to include these event-to-event interactions, augment the Poisson process with that type of dependency. It generates events in these causal cascades, these forward-rolling cascades. And it's important to note that the interactions are purely excitatory in this case. You cannot have a negative temporal or a negative weight or a kernel that decreases the rate. You run the risk of perhaps going below 0, which is required that obviously you have a positive firing rate for processes. So the question of inference is, given this model, this Hawk's process dynamics, and given some random network model, how do we infer that this particular chain, first to second, second to third, and third to fourth, is the correct set of interactions, or the best set of interactions to describe this spiking activity, when all of these other potential interactions could have existed? Or put another way, inference is the test of evaluating the probability of one story, one set of interactions versus another. So the probability that all of these processes or nodes are independent, that each is generating events from some background rate, versus a story that looks like this, maybe the one set of interactions versus some other
And that's pretty much the only thing that affects the rate.
Yeah.
Because you can imagine the rate, changing along, and you may or may not see a realization of that, and some covariates move that or something. This is
Yeah, exactly. So there's this trade-off between explaining changes in firing rate using previous events versus using the background rate, as I've been calling it. So you have this identifiability concern, perhaps, that you have a background rate which could vary at perhaps very fine timescales, enough so to capture all of the observed spiking activity. Um, in my opinion, I think of the background rate as something that perhaps could have these slowly varying things, but very slowly varying dynamics, but varying on timescales that are perhaps longer timescales than the spike or event to event interactions. So,
I mean, what about noise? I mean, I'm mapping this onto like international conflict events where it tends to be extremely noisy. And some events you can make the story that they're changing the rate of what's going on afterwards. But some of them are just noise. And they clearly would not change the rate of anything else and just make it harder for us analysts. And you have to start somewhere, so it seems like a reasonable place to start. But I wouldn't expect that the expected value would be a function of the noise. So in that case, you just use something. There's some analogy to the health process.
yeah, that's a really good point, and that's something that, as we'll see in the example, is definitely a confounding factor. How do you take homicides or batteries, which are completely unrelated to things, and somehow filter those out from the signal, right? And I think there's different ways of perhaps doing that. Perhaps you have some latent variable which says, is this event belonging to some noise process, or is this really something that is part of the interaction itself? The background rate, again, does give you some ability to capture all of the events that are not reasonably attributed to other proceedings.
And all of this is directed. There's no recursive element. There's no feedback, for the back end or one or anything like that.
So I've only shown one example here, but the model itself is completely flexible to capture that. So for example, one type of network model that you might use is something that forces the network to be symmetric. To say that if there's a contraction from A to B, then there must exist one from B back to A. That's definitely one hypothesis that you could build in. And moreover, you could have self-excitation, that the events on one node excite further events on that node and have this positive feedback loop. Actually, that brings up a good point about the stability of these processes. So there's a nice literature on how you make sure that the set of interactions that you have is not going to diverge off into predicting infinite number of infinite variables.
That would be a violent world.
That would be thankfully it's not always like that.
There's a lot of economic growth, man.
So, talk about what inferences means. How are we going to actually accomplish this? And the way I'm proposing to do so is using Bayesian inference. Thinking of these random network models as prior distributions over the interaction network, and then saying, given this prior distribution and the likelihood that's provided by the Hawkes process, can I infer a posterior distribution over network structures? So the Hawkes process is that critical link that provides the likelihood of the observable events. We can also infer the temporal kernels, the shapes of those kernels. The events have some very short-acting types of responses, or do they have some very long, prolonged interactions? And then one thing that I think is interesting is the possibility of performing model comparison. So saying, is this system better modeled using a symmetric random graph versus an Renyi graph versus some stochastic block model? What's the best way to really characterize the latent network of interactions?
Is there a trade-off here where you could, if you through other means than just the data, the point process data you observe, decided what you knew the temporal length of the kernels was, or the more generally what the density of the kernels was, that you'd actually get a better likelihood then on what or the likelihood would be more informative on what particular latent network is generating. Essentially, it seems like you're inferring a lot of things, and if you fix some of those parameters, you could get better inference on the other parameters.
So, yeah, that's definitely something you could do in this case, rather than inferring the temporal kernel shape. If you had some way of estimating it,
Okay.
maybe empirically going in and saying,
How long do
I
things
have
last?
expert knowledge about the stock market. I have
Okay.
expert knowledge about how interactions occur in Chicago. You could definitely fix that. And in practice, what we end up fixing is the length, the duration of the kernels. We're going to have kernels that have some fixed support, some bounded interval over which they can affect other events. And in order to set that, we do some sort of model comparison to evaluate which ones are better. So how do we actually go about doing this Bayesian inference? One approach would be to do something with maximum a posteriori, try to find the network. But that's a challenging thing when you have this binary network of is there or is there not in a connection between two nodes. What I'm proposing to do is to use Markov chain Monte Carlo to sample from the posterior distribution over networks. And the idea is very simple. We're going to invert the Hawk's process dynamics and add in these auxiliary variables, which are the parents of each particular event. And then given those parents, the Hawk's process likelihood will factorize into a bunch of independent Poisson processes. And give sampling, which is one method of performing Markov chain Monte Carlo inference, will become fairly easy. So I think this is something that can be illustrated fairly naturally using just pictorially here. So if we go back to our example of the Hawk's process dynamics, we thought about these events as being drawn from some preceding event or some background rate of the kernel. So the parent variables that we've introduced will really correspond to the coloring of the events here. And I should note I've changed the semantics a little bit. Now the color of the events is going to correspond to the color of the parent. So in this case, all of the events are currently attributed to the background rate, which is in parentheses there. But using this Poisson superposition principle, we can say that the probability that an event is generated by the background rate versus some preceding kernel can be evaluated just by looking at the relative height of the kernel and background rate at the time of that event. So we'll go through and sample a new parent for each event, which will correspond to a new coloring of events. Perhaps some of the events in this case get assigned to the kernels. This is something that can be done easily in parallel. One of the things you might worry about by introducing all of these per event variables is that typically the number of events is scaling much, much faster than the number of nodes in your network. So how are you going to ever achieve tractable inference in such a setting? Given that these events can all be done in parallel, we send it off to a graphical processing unit and just do these all simultaneously. To infer the strength of these interactions, or the weights of the edges or interactions in this network, we're going to leverage gamma conjugacy in this model. And basically the weights are going to correspond again to the scaling. And the weight that we sample will basically be biased by the number of events that are currently attributed to the interaction. So in the cases where there are very few events that are assigned to preceding kernel, then those interactions will be downweighted. And since we have this nice conjugacy, that's something we can do in closed form again with GPU. So we downweight some which are not currently being utilized. In this case, the interactions which were spurious and not part of the true model which generated these spikes. And then finally, we have this binary matrix of is there a connection from one node to another. this is the part that made the optimization, the map approaches more challenging. And the way that we're going to sample these is by collapsing out the parent assignments. This is something called collapsed gift sampling. And we're going to think about we're going to ignore the parent assignments and just think about the cumulative rate that's aggregated by the sum of all current kernels. Well, so what's the conditional probability that this interaction exists with the edge, or with this interaction, and then without it. And then we'll sample a new entry in that interaction according to that relative probability. And again, this is something that can be parallelized to some extent. All of the incoming interactions to a given node are independent of the incoming interactions to another node. So we can get a k-fold speed up on that sampling time. So again, these are all tricks that we might use to try to scale this up to really large settings where we have many spikes and many processes. So in this particular case, we went through and we removed the interaction from process 1 to process 3 because there wasn't a whole lot of evidence for that interaction existing. And then this sampling was repeats. So are there any questions so far on the sampling procedure?
Just general question, are the interactions always one way? Like, you can't go backward from like 4 to 3, or like, it seems to me they're all related and all arrows should go in both directions usually.
So that's related to the previous question as well. The interactions could go in both directions. There could be this feedback loop where the first process excites the second, and the second feeds back and excites the first. And there's no reason that the network cannot be structured like that. For simplicity, I've only shown a sort of a feed-forward type of network here.
So do you always have to sort of define a starting point in a sense? Like, sort of, how do you pick where to start, where the events start, right? So
Yeah, like, are you saying, how do we know that event 1 is like the starting point? If we're trying to infer everything about the graph, like, do we have to specify that?
So the parent variables that we're introducing here are really just auxiliary variables that are allowing us to have more efficient inference of the weights and of the temporal kernels, for example. So for each event here, the potential parents are going to be, so for example, this one here, the potential parents are going to be only the kernels which have some non-zero weight at that time of that spike. So it would be either this kernel or this one of the background rate. So I think it sounds like I don't think you should take the parents necessarily as too seriously. They're more of a auxiliary variable which we can use to make our subsequent inference more efficient. But you're right, in some cases, the first event can only be attributed to the background rate because there were no preceding events in our data set that could have parented it.
So how should we think about uncertainty over the network, right? So is it just continuous weights and there's something like a credible interval around the weight for each connection, or?
So under the model, it has
Yeah.
a prior distribution over the networks and prior over the strength of interactions. We can compute the posterior distribution over the strength of these interactions, which will give us not only some mean value of the weight, but also some confidence intervals per se.
Okay, because it would seem like in most data sets, there's gonna be a lot of very similar networks that could have generated the data, and that okay,
that is a good point. And this is something that's difficult in general, right? And
right.
So your prior distribution over the networks and over the temporal kernels will have a significant effect on what types of networks that you get out in the end. Anything else? So I've kind of ignored the background models up to this point and used perhaps the simplest background model. So that's just time homogeneous Poisson process. We can get considerably more sophisticated depending example, as we'll see in Chicago, background or the overall rate of incidence has a very pronounced seasonal effect. So this is something that we can capture, for example, with the Gaussian process using periodic kernels. We can use Gaussian processes to model other smoothly varying external effects. Or as was pointed out, what if we have external covariates about the firing rate or the rate of events? And in that case, we can use a generalized linear model to link these covariates to the observed firing rate. And the approach will be very simple. Basically, if we have covariates x1 through xm here, or in this case just one covariate x1, we'll have some linear function of those covariates, and then pass that through an exponential nonlinearity to get a rectified firing rate, something that's always positive. So with that,
So, back on the slide. So it seems like most of this model is built on this idea that you have sort of one kind of event that can have varying degree to it, right? And I'm wondering, it seems like an alternative to just doing this sort of linear model with covariates would be, it seems like you could actually incorporate sort of a second kind of event as well that had, instead of like whatever the Poisson decay that you were modeling, say it has some other form, and it seems like you could just add that into the network, so that process one would have sort of implicitly two sets of things going on. They could feed to each other and they could feed to the other nodes. Is that the right interpretation of what's?
well, that's a really good idea. It's not something that I've explored up until this point, but what you could imagine is that we don't actually know the node on which this event occurred. We don't know that this event corresponds to, for example, the Apple stock, but that maybe there are multiple Apple stocks that each have different interactions with other stocks, or different kernels that they're associated with. So that could be another latent variable that's assigned to each event.
So can you incorporate covariate in such a way that it affects the probability of interactions rather than just affecting the baseline rates?
That's also a really good point. So you could imagine that one of your covariates is this event history itself. And that's something that's used in neuroscience as it's called just simply generalized linear models for point processes. One of the nice approaches about the Hawkes process is that you have this very nice auxiliary variable formulation where you think about the parents of each event. And I think that it also allows you to model systems which you think are mutually excitatory as opposed to having perhaps excitation and inhibition. So it's really a question of what types of things do you expect, are you trying to capture into this model? But that's a very good point there. Okay, so we talked a little bit about how inference might happen, how we could use different network models as prior distributions, and what types of models we could use to capture these background fluctuations or background rates of events. So let's take a look at how we could apply these. So the first example that we're looking at is trades on the S&P 100. And these are 100 stocks. Individual trades are collected at 1 second resolution in actually order book format. And we're only going to look at 1 week of events in September 2009. So this was back during the financial crisis. So there's a couple things a couple effects of that you might observe. And we're going to define ticks as changes in price of 0.1%. So we collect all these order book entries, when does the average price at some 1 second of time jump by plus or minus 0.1%? So the raw data looks something like what's shown over here. You have this stream of upticks and downticks that are going on. Some stocks are much more active than others. You might be able to observe some sort of events if you stare at it long enough, as I have, where all of these stocks seem to dip at the exact same time. And if you look at just the raw cross correlation between events on different processes, then you see something like this. Now, one question that often comes up and that you could ask about as an alternative to the Hawkes process, could we just look at cross correlation and maybe threshold some of the same problems. It doesn't have quite the same generative model feel to it. So it doesn't give you the same story of interpretability of the results that you get out. And as a baseline, what we'll do is look at this is the empirical firing rate on the left here in blue. And what you see is that at the beginning of each day, there's a huge burst in activity. There's upticks and downticks going on crazy at the start of the day, when it generally tapers off to the end of the day. Every once in a while, you do see these brief blips where there's some surge of activity that's perhaps related to some external event going on. If we try to model this with just the simplest approach that says each stock is modeled by a time homogeneous Poisson process, then what we get out is this red rate here shown. This is the aggregate of the sum of all of the stocks. Now, I haven't introduced this KS test, but this is basically just a way of asking how well does this model, the time homogeneous Poisson process, capture the observed activity. And the way that it does so is by saying under a Poisson process assumption, the interspike intervals, or the inter-event intervals, should have an exponential distribution. And we can actually go and see under the predicted rate how well do the inter-event intervals match that. And so the time homogeneous Poisson process doesn't do a particularly good job. In particular, there's a much higher prominence of short bursting activity than is actually observed.
That's good. So, when the stock market closes at what, 4 o'clock?
9:30 to 4.
9:30 to 4, right? But then there's lots of activity that's going on before, and you can actually see what those prices are, but that's not in this table.
That's correct. So we've taken out the stuff that happens after 4 p.m. And the reason for doing that is that those seem to be outlier events in particular. The prices associated with trades that occur after the close of the market are typically way off the mark from what's going on at the rest of the day.
But they're pretty close to what things open at. In fact, like that's by definition what things oftentimes open at.
So you're suggesting that you could look at these events that occur overnight, basically, and perhaps place the change in price at some point that's between 4 p.m. and 9:30 as opposed to 1 p.m.
Right.
That's
And that might
something
smooth things out as you get closer to this homogeneous process.
Well, I don't think
I don't know
that's,
that it's.
I don't know that that's actually happening. I spent a fair amount of time looking into that activity and decided that, at least for this example here, that it was too noisy to really make use of these interactions. But yeah, that's it.
But is that because the markets are too thin or something? I mean, what's the?
Well, I don't know
Most trading
exactly.
activity takes place in the first half hour. Almost all the volume
So it's
happens
it's
over
too-
the
okay.
So, as you said, perhaps there's just not enough events, and perhaps the prices associated with them are more variable than that. But that's something I'd have to talk more about offline, because I'm certainly not a finance expert necessarily. So it's
My wife.
So one of the things that seems pronounced as we've been talking about is that there is this time of day dependence. There's a lot more activity in the morning than there is in the evening. That's something we can build into the background rate, and we can do so using, again, this generalized linear model framework. So one of our covariates will be time of day, modulus of time over the beginning of the start of the day. And what we can capture with that is this, what's shown in red here, the exponential decay pattern as a function of time. But it doesn't have the ability to really capture these differences in how quickly that decay occurs, or especially these pronounced bursts of activity that seem to come some random offset from the beginning of the day. And we can see that in the KS test. In particular, we have a better fit, but it's still not particularly great. So the final thing that we'll try is using the Hawkes process for the stochastic block model. And the stochastic block model will say that each stock will have some latent variable, which is what block or cluster that it belongs to. And that the probability of connection between two stocks is a function of those block assignments. And immediately what we can see is that the Hawkes process can capture this bursting activity substantially better than just the simple background model. But then still room for improvement here. So I haven't pursued, how we can perhaps build in some external information that could account for this. Most of this lack of fit is coming from this excess of first ring activity. We still can't seem to account for it using this spiking activity. But that's something again that I'm looking forward to talking with hearing suggestions about what we might build into the model to improve that. But first, what I'd like to do is look at the block structure, because a big part of the story is how these random network models actually help us. And if we look at just the interaction network itself, not a whole lot jumps out at us here. These are a network of interactions between individual stocks. If, however, we look instead at the stochastic block, or the block structure that we've inferred, then things start to become a little bit more clear here. And what I'm showing is a matrix in which the entries show how frequently two stocks were assigned to the same class in our samples from the Fourier distribution. And
So the horizontal axis is the same as the vertical?
yes. Sorry, I just didn't include the axis.
And why are some of the, like, why is utilities narrow and vertical wide?
So there are only a handful, maybe 5 utility stocks, whereas
So each row of pixels is one stock.
each row of pixels is one stock. Yes. And I've organized the rows such that all of the utility stocks, the 5 rows corresponding to utility stocks, are aligned on top of each other.
You made a block based on those substantive distinctions.
Yes. So the red lines are showing the distinctions as Bloomberg, or I should have said this, as Bloomberg would describe them. And then we're looking at, under the posterior distribution, how well do our inferences about block affiliation match what the experts would say. So this is really asking the question of, do utility stocks have similar interactions to other utility stocks? Or should we think about consumer staples and consumer discretionary as being perhaps one that helps a lot here? And again, it's a little bit noisy, but if you look at the big blocks that occur along the diagonal, you can see that some sectors are generally grouped together. Healthcare and utilities and consumer staples get grouped into one. Now, again, I'm not capable of telling you why necessarily the interactions that are going from healthcare and other stocks are similar to those that go from industrial or telecom. But this is something that the model is picking up structure on, and would require some further exploration to really go and see what's going on there.
Sorry, the inference is that their trading volumes are similar at the same time, or is their price movements the same?
So trading volumes in this case, and that's again something I should. So and that's not quite true. So the inference is that the interactions, the block model says the probability that one stock interacts with another stock is a function of the block to which those stocks are assigned, and it's saying that the pattern of interactions between healthcare and other stocks are similar to the pattern of interactions between utility stocks and other stocks. So that's why they get grouped together into these different clusters.
Is that typically something you care about? I mean, so the fact that something there's a heavy trading volume on healthcare stocks and there's a heavy trading volume on utilities at the same time, or whatever, is that something that an estimate of interest for us in financial econometrics?
Well, I think that it does give you a story for how to. It gives you a model that allows you to perhaps predict subsequent activity. So if you have a good reason to believe that in the past there has been this pattern of interaction, then that could potentially carry over into making future predictions.
Sorry, maybe I'm confused. So I thought it wasn't volumes. I thought it was. I thought the spikes were changes of 0.1%, right? So then it would be like interactions of movement in the stocks.
Okay, sorry, I should have clarified. That's good.
Okay.
So we took all of those upticks and downticks and combined and ignored which direction the jump happened, and we said there was a change in price of 0.1%.
Okay.
And so that's going to be the actual technical definition for this.
So this isn't like volume of trades. It's change in price. It's
Right.
some absolute magnitude of change in price.
So does that mean healthcare and something else, the darker cells could actually imply that they're moving in different directions?
Yes, so this is not capturing any directionality of price movement in this case.
We'll
It's
stop
one
by
way.
healthcare and buy most vehicles.
So there's an
So I've either got to buy or sell healthcare when something else is moving.
So there's an easy way to capture this. So the idea would be you place upticks and downticks as separate processes. And I haven't done that for this slide, but that's
Okay,
something that you could do. What you would find is basically that upticks on one stock are the best predictors of subsequent downticks on the same stock. So the stock goes up, stock goes down. And sometimes there are these really large fluctuations. But you can still see even in that there are these sector level interactions. Again, financials, some IT papers. So what other questions, and we've already raised a couple of really good questions. What other questions could we ask about this data set? One is the prediction story. How well can you use this model to predict subsequent activity? Another is what is the relevance or significance of asymmetric connections? Does Google always drive with Microsoft? And does Microsoft reciprocate, or is it one way? And then again, what covariate information? So another example is that we started out by motivating is looking at gang violence in Chicago, which is now a spatiotemporal process. And this is just a scatter plot of all of the homicides in red, and then also the battery with a deadly weapon, which seems like the next worst thing to me. It's black. And some, yeah, and there actually is some, at least anecdotal evidence to suggest that battery with a deadly weapon is also highly correlated with gang violence. Some foresaw that WBEZ, which is the same radio station that does Wait Wait Back Home, went through and created this awesome Google Maps KML file, which shows the police reports of where gangs actually exist, and we can find them. They converted this to a form that we can consume here. So the idea that is going to be assign each of these events to the gang region in which they occur, and then ask, do events in one gang region incite subsequent events in other gang regions? That seems to be, according to police documents, sort of the definition of gang warfare. So is that something that we could potentially pick up with the Hawks process? If we look at the temporal rate of events here, we see that seasonal effect that I was describing. Basically in red at the bottom are homicide rates, empirical homicide rates, and in blue are the battery with deadly weapon. And we see that there is this this also overlying trend or decrease in the rate of battery with a deadly weapon that's occurring over 10 years of getting moved out. I'm hesitant to say whether that's actually a decrease or if that's a reporting artifact, but that's what the data looks like. And then we also notice that there is inhomogeneity throughout the course of the day. And I apologize if this isn't isn't brighter. But basically it's showing that there are very few events that occur at 6 a.m. Most of the event activity occurs from noon until midnight. So that's also an important thing we can build in.
Safest time to walk on the street.
That's right.
6 a.m.
Go to work early. So the baseline model that we'll use is a vectored spatiotemporal Poisson process, which has no Hawks interactions. So our covariate information will be time of year. Sorry, not time of year. Our covariate information will be temperature, which has a very periodic effect throughout the time of year, and is able to capture this oscillatory and periodic behavior in firing rate. And it will have the time of day, and it will have the overall time dependence to capture this linearly decreasing trend. And immediately what we see is that the simple GLM model, which doesn't have any event-to-event interactions, does a very good job of characterizing the events, at least in terms of matching the inter-event interval as predicted by the Poisson process.
Does that predict, is that an in-sample fit?
Yes. But this is not showing predictive like this. I have some of that, which I'll show in a second.
So just the fact that you're using basically the last observed point, which is basically the error, that's going to make it fit, right? Even if the covariance sometimes
So the covariance so there's no event-to-event interactions in this model here. This is simply saying that all of the gang regions have a shared background rate, which is a function of the temperature on a given day and the time of day, and the time since we get the data set. So no event-to-event interaction.
No time series process.
So
You're not using the past.
not using past activity in this case. So it's suggesting that the simple model that doesn't factor or take into account interactions between gang regions could potentially be enough to capture the variation in the observed.
That's not, how does it, that people only kill each other in Chicago in the summer?
In the summer.
Oh,
Violence.
That's an ice
Being
bucket.
killed in the cold.
We don't count them.
Yeah. Yeah, so it's very remarkable how pronounced that seasonal effect is. And actually, one of the anecdotal things that comes out of Google searches for this is Memorial Day weekend is a particularly bad weekend. It's like the beginning of starting the season. So, and
Labor Day.
you know, just Labor Day, I don't know. But yeah. So we can still build in the Hawks interactions and see, can we pick up on interactions between different gang regions? And here I'm showing just a sample of one sample from the posterior distribution in which are the strongest interactions. And you can ask, do these interactions that we predict or infer correlate with the different high-level nation affiliations of these gangs? The gangs are organized; they have some higher-level nation cult of people with which they're affiliated. It seems that the interactions do not have a strong correlation. The inferred interactions do not highly correlate with what the police have called or determined these nation affiliations to be. And if we look at predictive capability between the Hawks process fit on data from 2001 to 2011, we ask how well can we predict data from 2012, we see that the Hawks interactions don't really bias, or don't bias anything. There's an insignificant decrease in predictability using the Hawks process. So how do I interpret this? I guess I would say that the excitatory interactions do not seem to improve the prediction, which suggests that maybe homicide and battery with a deadly weapon are not the best indicators of gang violence. And maybe that if these interactions do exist, as police reports suggest, that there is some other, that they manifest in some other way.
So you have the geographic data you have. You said it came from like a particular moment in time, right? Like that it was. And so you have 10 years of data here. Presumably, like the territories of the gangs shifted over those 10 years. So is it possible that the reason you're not picking up much from the second model is that there's just a ton of noise over the 10 years, and that the like mapping of where the gangs are, whatever year that was done, like 2011, it doesn't map very well to 2001 and 2002.
That's a really good point. That these gang wars could perhaps be changing over the course of years, and that if you look at the police reports for where these gangs existed in 2001, they're not in Google format, but they show a slightly different story than what you see here. The high-level story is still West Chicago and South Chicago are regions of high gang intensity, but down to the individual blocks at which these gangs exist, that is very likely changing. But again, that's something that could be modeled using a more sophisticated machine.
It also seems like you're conflating sort of regular crime with gang crime, and so you should just call like victims rather than gang affiliates.
So,
Yeah, I mean, if you have like, most domestic violence isn't drive-bys, right?
okay, so
If you have information about the nature of the homicidal
to
act.
go into a little bit more detail on the event, so it's available publicly from the city of Chicago on the they have a very nice website for it, and you can filter out. And I have filtered out battery with a deadly weapon that's not flagged with like domestic violence. But as we were talking about before, we still have these events which we can't really ascertain did they come from gang violence or not. And so that could be one reason that we have difficulty pulling out some signal. Perhaps there's a lot of noise here. Now, There has been previous work using Hawks processes in this type of way, just looking at gang violence in Chicago. But the data that they used was actually highly scrubbed. Somebody was in the field for a year, marking individual events with which gang was the aggressor, which was the one who was attacked. So we don't have any of that here. So this is more of a field test of can these methods be applied off the shelf in a way that's useful to Chicago Police Department without having to invest agents to mark everything. Yes.
I guess I'm curious how this gang violence in Chicago research relates to some of the work that's been going on in LA for some time, using very similar methods.
Yeah.
The Moeller lab and all those guys who basically use Hawks processes for LA crime data.
Yeah.
So I was wondering where your method fits in with what they're doing, and if there are any sort of key substantive differences between your approach versus what the Predpol guys are doing in LA.
So I'm familiar with that work. My take on it is that they not really emphasize the network aspect of things. They don't really go in and say, if I knew, for example, that gang interactions occurred with some characteristic distance scale, maybe only neighbors affect, but that could perhaps be the key insight that would allow you to filter out some of these noises. That would be a fairly informative prior that could be useful.
Because if I'm right, from memory, I think they do find that the Hawks process improves fit substantially over the homogeneous Poisson in their applied example with the LA data.
Yeah, that's true, but that's using this data that's been scrubbed by somebody who's out there in the field marking and making sure that there were very few spurious examples in that data set. So I would be excited. I would be interested to see how that would apply in these cases, or would pick up on it. But the methods are quite similar. They just do not emphasize the network to this data set.
And then I guess going back to the financial data, the nodes, so to speak, in the gang violence network are tessellations or grids of land, right?
Yeah.
Whereas in the other case, we observe the actual firms. So we're comparing the rates across territories in this case.
Yes.
Right.
And so there's other ways you could say that homicides have some spatial effect. The actual location in which the homicide occurred maybe excites other homicides nearby. I have found that more difficult to formulate in a way that seems compelling.
I see.
So next questions. If it's not observed in these mutually excitatory patterns, then what are the manifestations, and could we capture those in this model in a reasonable way? And then we're looking at predictive power over the course of an entire year. Maybe over the course of the year there are times that are highly Poisson, but other times, Memorial Day weekend, for example, could exhibit more bursty types of activity where these interactions would be more visible. But just to conclude, so in many cases of interest, we cannot directly observe the networks that we're interested in reasoning about. And Hawks processes combined with random network models give us a way to join these two fields into one coherent probabilistic model. And the Poisson superposition theorem and the mutually excitatory nature of Hawks processes gives us a very natural and elegant auxiliary variable formulation. MCMC is fast and tractable using these parallelization techniques, and it lets us reason about hidden path abstractions. Thank you very much for listening and your comments. So, thank you.
Thanks so much, Scott. We'll open up the floor to questions, and feel free to
It seems so. The Chicago example kind of brought up. There's still actually at the interplay between inferring that your model is doing something reasonable and inferring things about the world. I was curious if you thought there were domains where, so essentially you looked at whether your model matched up with what police reports seemed to say, and said, well, the model's not really doing it right. So are there domains where you're more confident saying that the experts don't understand some important part of the process, or do you see this more as something that always needs to be benchmarked against experts in the domains that you're familiar with, and would simply be like a way of reducing analyst load going forward or something like that, which is kind of how you framed the LA Chicago police thing.
Yeah, one of the really exciting possibilities is if this model really captured interactions in a way that seemed meaningful, then you could come up with interventions, come up with strategies for how to adjust your resources in a way to perhaps counteract that. And I think that would be a really useful application of Fox processes. At this point, I'm hesitant to say that the police are wrong in saying that there are interactions when there really aren't. I suspect that more realistically that these interactions occur in some way that's perhaps more subtle or that is perhaps not reflected in this current data set. So, you know, though the result is a negative one in terms of having Hawks process interactions and improving performance, I don't think it's necessarily saying that these interactions don't exist or that Hawks processes aren't useful, but rather that we have to be somewhat wary of just taking these complex models and throwing them at validity data and interpreting as good interactions as meaning something that can be played in more parsimony as well. Yes?
Question about how to compare these models. So in the case of the stocks, you gave a KS plot and you say, well, okay, this model doesn't fit very well, this other model fits better. But the models that are fitting better, I'm guessing they're fitting with more parameters, right? It's a more complicated model. So how exactly should we think about trading those two off?
That's right. So, I mean, the KS test is one tool for evaluating goodness of fit, and I think it should be used in conjunction with these predictive likelihood plots that I think they provide two different insights into how good the model is. Unfortunately, I didn't show them for the financial case here. It's something that I'm actively working on. But yeah, so the KS test is really just evaluating how well does the interspike interval match. The predictive test would say, using cross-validation, how well does this model predict unseen data? How well does it generalize? So I think in many cases, Fox processes and similar models have been used and evaluated solely on the basis of these KS plots. But really, we should be using spectrum assessments.
So going on that question, so it seems like when you're comparing the models, you're comparing the Hawks process to like a GLM, like a basic GLM, sort of the baseline. But I was wondering how it would compare to like, say, you did a GLM with spatial lags or temporal lags, or like sort of like spatial weights that people use that are sort of slightly easier to implement.
Yeah, so that is also what's known as the GLM and for point processes and it's used widely in computational neuroscience, for example. I haven't done the comparisons here, but that's an alternative way that you could look at this model, or try to fit this data. The interpretations would be a bit different. And that would say that gang violence in one region actually inhibits violence in another region, which
Right. So you'd be putting some structure on sort of how much a neighboring region affects your region. Like that's so sort of you would be imposing a little bit more structure.
we could impose structure in the GLM in a similar way using network models. And that's something I've actually worked on in other work as well. You could also do it in a very hard constraint way. Say I'm only going to allow covariates that come from similar or nearby gang regions or stuff. Hard coding network systems.
Are there any other applications you're considering at the moment? What other types of data are you curious about?
Well, so my primary research area is in computational neuroscience. So thinking about how spikes in one neuron are affecting spikes on elsewhere in the brain. And in that case, I really think the network structure is a very important piece of the story, thinking about how different brain regions connect. This foray into finance and into crime in Chicago is somewhat of a step outside of my primary field, but I also think that these methods could have very broad appeal. So finding other applications for that, I'd be happy to hear if anybody else is excited to try these out elsewhere.
Yeah, I've done a little bit of work on sort of refugee movements resulting from violence. I know there's other people, particularly in the government department, who have done a lot of work on that, where you end up with sort of
likes on Facebook.
Like, yeah, Twitter tweets and stuff.
Yeah. Or no, I mean really, right? Like if
Yeah, because that event actually.
exactly, it posts it and makes it public for others to see. And
Well,
then-
it becomes real.
yeah.
Right.
Yeah, from there you have some, again, some social network structure that you can actually leverage.
Is Galton Watson, is that a special case of this, where you're looking at family names and how they descend? Is that I thought that the Hawkes process was sort of generalisation of this. So they were very worried about family names dying out in Victorian Britain, and so they sort of said, well, let's, because if men don't have enough sons, then these names will die out. We'll be left with no names. And I just wonder. I thought this was a generalisation of that process, in which you have people meeting, and then you want to know how many sons do they have, right? So
I don't know that particular process, but it sounds very similar. One of the ways that the Hawkes process, another name for it are these offspring.
Right. Yeah, I guess. Okay. So I don't know. You could look at like.
So what was the answer?
So it depends. So in countries like Korea, there are very few last names. That's something to do with this process. Whereas yes, in Britain they're not rare. So I don't know. It's like rare names will die out because I don't know. I'm doing my best, I guess. So the other thing, I don't know. So anything I guess where people are meeting and reproducing, I guess. So eHarmony or something. But I guess they don't give their data out.